Hey, now we're going to talk about models of the atom and energy level diagrams. In order to do that, we kind of have to talk a little bit about the history. We're not going to go all the way back into all the different models of the atom. We'll kind of start with the Rutherford-Bohr model and go from there. And we have to pay homage to Rutherford's gold foil experiment because it did revolutionize our thought processes on the atom. And what he did was he shot alpha particles, which are a positive helium nuclei, at a thin sheet of gold foil. He used gold because it's easy to machine, so he could get something that was only 4, 5, 6 atoms thick. And what he thought was most of the particles would go through and some would be slightly deflected. And it's actually two of his assistants that get more of the credit than anything, because what he had was the gold foil set up, and on the other side of it he had a film so he could detect the alpha particles. Well, two of his assistants said, well, listen, why don't you completely surround the alpha emitter with photographic film so you can see what's exactly happening. Otherwise he probably wouldn't have checked, because what he found out was, yes, most of the particles went through, but some particles actually completely reversed directions. And that kind of amazed him. The quote he used was, it was like shooting a cannonball at toilet paper and having it bounce back. What that led to him was the conclusions that you see. Atoms have small positive centers, take up less than 1% of the space of an atom. Atoms are mostly empty space, therefore, and electrons orbit around the nucleus. Now, there's a couple problems with Rutherford's easy explained model, and that's the fact that electrons do remain in orbit. Remember, electrons are negative, the nucleus is positive. They should crash. They don't. Why? Second thing is electromagnetic radiation occurs only at specific frequencies, and we'll talk about more in just a second about that. Now, the Bohr model added a little bit to that. He said the nucleus was at the center, but then he said electrons can only exist at discrete energy levels, and each atom only allows a certain number of specific orbits or electrons per energy level. And I know you've talked about that in chemistry. From a physics point of view, probably what's most important is the fact that electrons can change energy levels. And if they absorb a photon of exact energy, they jump to a higher level. And then when they jump back, they emit a photon of that same exact energy level. Now, some of the Bohr successes. Number one, they predicted the energies of photons emitted and absorbed by hydrogen, which was heavily studied. It also explained the limitations of the Rutherford model, and for that he was awarded a Nobel Prize in Physics in 1922. And I'm pro Niels Bohr, by the way. He's Danish. I'm pro-Danish, so therefore I like Danish people. So what we have is an energy level diagram that looks like that. The ground state electron, and this is an energy diagram for a hydrogen atom. At the ground state, the lowest energy level, that's where the electrons are normally. Well, I can make those electrons jump to higher levels by adding energy to it. Now, they're not stable there, so once they jump to that higher level, they will jump back down initially. So, and we know for a while that if you shine light on atoms, they can absorb photons and increase in energy. You can also cause them to increase in energy by electricity and heat and other things. But we're primarily talking about light creating light. So they can absorb photons and increase and go to a higher energy. The green line you see is a photon being absorbed. So the electron jumps to a higher level. So, and the one that's shown is an 8 electron volt photon hitting it. So therefore the electron gains 8 electron volts of energy. And then of course you can use Planck's equation, E equals hf, to calculate the frequency and wavelength of the photon. So let's do a practice one. Let's calculate the energy and wavelength of an emitted photon when an electron moves from an energy level of 1.51 electron volts to 13.6 electron volts. So E is equal to delta E. It's the change in energy. And here's the thing, is it really doesn't matter which direction you go in. The positives and negatives indicate whether you're absorbing an electron or emitting an electron. So the energy of the photon is 12.09 electron volts. So that's the photon energy. E is equal to hc over lambda. Remember, we can use the shortcut equation. Solve it for lambda. It's hc over E. 1240 electron volts times nanometers divided by 12.09 electron volts, 102.6 nanometer. Excuse me. We're familiar with the emission spectrums that look like this. You've looked at these in chemistry before. And again, what you see are lines that correspond with those electron energy jumps. So when an atom emits photons, it glows. The photons cause bright lines in a spectrum. This is called an emission spectrum because these are light that is being emitted. And again, if I heat something up, it makes it more obvious that I can see it. But I can see it even off things that aren't heated up or anything. Now, emission spectrum always involve going down in energy level. So when the electron goes, by the way, that should be electrons going down in energy level, not atoms. So as they jump down, they're going to emit photons, and because there's only certain individual energies associated with that, there's certain individual lines that are given off and colors given off. Since every element is unique in its electron structure, it gives off a unique spectroscope model. So what is the frequency of the light that will cause an atom shown from the transition from the ground state to the first excited state, and then draw the transition? Well, I think it actually makes more sense to draw the transition first. I think it's easier to see, and what happens is now we attack it. We know that E is equal to 6 electron volts. So we have a photon coming in. The arrow going up means it's coming in. It's gaining energy from that photon. Now I'm going to say lambda is equal to hc over E, that 1240 number again, divided by 6 electron volts, 206.7 nanometers for the wavelength of light. Now here's a way to do it in 2 steps. The delta E is equal to E final minus E initial, 6 electron volts as you've seen before. E is equal to HF, so therefore F is equal to E divided by H. Use the electron volt value for H since you have electron volts, and I get 1.45 times 10 to the 15th hertz as the frequency. Then I can use C is equal to F times lambda. Lambda is equal to C divided by F. I get 210 nanometers. The only difference is that's rounded off more than the other value. It's still equal to what the initial value was. So that's another way to do it. Remember, the hc over lambda is just a shortcut equation that combines E equals hf and C equals f lambda. And there's again a picture of it. What is the longest wavelength of light that when absorbed will cause the atom to ionize from the ground state? Well, obviously it's going up to the top level. E is equal to hc over lambda. So lambda is equal to hc over E. By the way, the 4.14 and 3 times 10 to the 8th numbers put together give you the 1240 electron volts times nanometers. You get 108 nanometers. Excuse me. The atom shown is in its second excited state. What frequencies of light are seen in its emission spectrum? So it's at the -3 electron volts, second excited state. Draw the transitions. Well, let's look at each one. So obviously I can go from second all the way down to the ground level. From second to ground, it's an 8.5 electron volt photon being given off. F is equal to E over H. There's E, there's H. 2.05 times 10 to the 15th hertz. The next one is when I go from the second excited state to the first excited state. That's a difference of 2.5 electron volts. So therefore the frequency is 6.04 times 10 to the 14th hertz. The third one is when I go from the first excited state down to the ground state. So in other words, it can go from the second excited state down to the first excited state. It'll stay there for a millisecond. And while it's doing it, as it goes down, it emits a photon. Once it gets that first excited state, it will then eventually jump back down. So I can have 3 potential different lines that I'm going to see.